Now it's time for the ideal gas law. So, treating a gas as if it's an ideal gas is the way that we deal with all of these calculations without losing our minds in the process. So, if the temperature is high enough and the pressure is low enough, all gases behave ideally. And what it means to behave ideally is that the volume of the gas molecules is negligible. So the volume of that tiny tiny sphere that is my atom of gas or part of my molecule of gas, that volume is negligible. The molecules exhibit continuous random motion, and the molecules are non-sticky hard spheres. So if you've taken physics, the non-sticky hard sphere probably sounds familiar. If you haven't, all it means is that if my gas molecules run into each other, they're not going to stick together. They're just going to bounce off of each other, like if two pool balls ran into each other. Ideal gases also obey several laws. Now, normally, the way that this is taught and put together, and what you will see in the reading, is that you'll come up through Boyle's law, Charles' law, Avogadro's law, and in the end, they will give you the ideal gas law. I'm gonna give you these equations, but you'll notice these are not on the equation sheet. I do give you the ideal gas law on the equation sheet because the ideal gas law is just going to be a combination of these three laws, and these can be derived out of the ideal gas law equation because they were used to make it. So the laws that ideal gases behave, Boyle's law relates pressure and volume. So if everything that's not listed here is held constant, so you have the same number of moles and you have the same temperature, the pressure and the volume under one set of conditions, you can find the pressure and volume under another set of conditions. So same number of moles, same temperature. If I have a pressure and a volume and I change the volume, I can find out what the new pressure is. Charles' law relates volume and temperature. So my pressure and number of moles would be held constant if I'm dealing with Charles' law. And I could look at how changing the temperature changes the volume, for example. Avogadro's law relates volume and number of moles. So now pressure and temperature are being held constant. And if I do that, then I can see how changing the number of moles would change the volume. Now, if you put this all together, it's PV equals nRT. P is my pressure in atmospheres. V is volume in liters. N is moles in moles. T is temperature in Kelvin. And you know that you need these units because the gas constant R has units of liter atmospheres per mole Kelvin. And that value is 0.08206. Okay, we're going to do an example. I have a really important statement here. So there's an entire section usually on stoichiometry and gas reactions. You know how to do this. I just want to remind you, you do know how to do this. It is still just mole ratios. We may just have to do some other things to figure out how many moles there were or are. Okay, let's try it with an example, which says, what volume in liters of hydrogen gas at 355 K and 0.971 atmospheres do we need to synthesize 35.7 grams of CH3OH? And you get a balanced reaction here. Hopefully it's balanced. So CO gas, so carbon monoxide gas plus 2 H2 gas makes CH3OH, which is also called methanol. So I have my balanced reaction. I have a specific amount of product that I want to make. I want to make 35.7 grams of CH3OH. So it's asking me what volume of H2 I need. Well, I mean, if I know how many moles of H2 I need, then I can calculate the volume. But first, I just need to figure out how many moles that is. So in terms of a plan, I'm starting with grams of CH3OH. I know that I can convert grams to moles for CH3OH. I have the formula, I can get the molar mass. And then I have the reaction, so I know I can go from moles of CH3OH to moles of H2. And then H2 is a gas. I will know moles, I'm given temperature, and I'm given pressure. So I can solve for volume using the ideal gas law. All right, let's give it a try, put it all together. 35.7 grams of CH3OH. This is a molar mass of 32.041. So that would get me to moles of CH3OH. And then every 1 mole of CH3OH, I need 2 moles of H2 to make that happen. So I need 2.23 moles of H2. Now, I have the moles. I want to know the volume. So ideal gas law, I've rearranged it to solve for volume. So I'm looking for nRT over P. Moles is what I just found. That's the 2.23 moles. R is a constant. The temperature was 355 Kelvin, and the pressure was 0.971 atmospheres. So in the end, this gives me 66.85 liters of H2 that I would need in order to do this reaction as requested.